All right, in the second part of 3.2, we're going to take a look at zeros of polynomials. A the first idea is that a polynomial of degree n has at most n real zeros. So if our polynomial is fourth degree, we say it has at most four real zeros, right? Now, the zeros of a function go by lots of different names. I mean, some that we've used before are solutions or roots. Okay, so this next little section just says if f of c equals 0, then lots of things that mean the same thing occur. We say that c, that value that we plugged into the function and got out 0, we say c is a 0, we say c is a solution or a root. We say that c is an x-intercept of the graph, which means the point c0 is on the graph. And then this last one, this is going to be important for our lesson today. That means that x minus c is a factor of my equation. Okay, so this part is important, the minus c, because what we're saying is if I were to take that factor and set it equal to 0 and solve, well, I would add c to both sides and I would get x equals positive c as one of my solutions or roots or x-intercepts. So x minus c would be a factor of the function. So let's talk about multiplicities of zeros, and then we'll take a look at some examples. So the number of times a zero appears in the equation is called its multiplicity. Now, if you add up all of the multiplicities of all of the zeros of a function, it will be exactly the same as the degree of the function. Okay, now for everything that we're going to look at in this section, we're just going to deal with real zeros, but this will eventually, once we get into the next couple of sections, will include real and imaginary zeros. All right, now a zero with odd multiplicity will cross the x-axis. What that means is if that zero shows up 1, 3, 5, 7, and so on times, the graph will cross the x-axis at that zero. But if my zero has even multiplicity, so if that zero shows up 2, 4, 6, 8 times, then the graph will just touch the x-axis. Okay, we can think of it as like bouncing off at that point and turning. And another more mathematical way to say that is it's tangent. Now, the last idea here is that a polynomial of degree n, the graph will have at most n minus 1 turning points. Now, for example, let's say we have a third degree function. So a third degree function could look something like this. Okay, the turning points are these guys right here, okay, where we change from increasing to decreasing or decreasing to increasing. So here, this is a third degree polynomial. It has two turning points. Right, so that's an example of what that last idea means. So let's take a look at a few examples here. Right, we want to find the real zeros, state the multiplicity for each one, and then state whether the graph crosses or touches at each zero. So these are all factored for us already. So in this example, I'm thinking about taking each of these factors and setting them equal to 0. Right? So x minus 1 equals 0. Well, I would add 1 and get that 0 is x equals positive 1. Same thing here, right? I'm setting x plus 2 equal to 0, subtracting the 2 over, and I'll get x equals negative 2. And for the last one, x minus 3 equals 0, add the 3 over, and we get x equals 3. Okay, so when you're doing problems like this, you don't need to show this work. Okay, I just want to ingrain it into your heads that this is what's happening. All right, so for each of these zeros, this x equals 1 has a multiplicity of 1, because even though we don't see an exponent, we know that each of these exponents here would be 1. So the multiplicity is 1. So that means that the graph will cross the x-axis at x equals 1. And it'll be the same for each of these because the exponent is 1. So that means the multiplicity is 1. So the graph will cross the x-axis, and the multiplicity is 1. So the graph crosses the x-axis. All right, let's try another one here. All right, on this one, we only have 2 zeros. So this first one, we'll get x equals -1 when I set this equal to 0. The multiplicity is just 1, which means the graph crosses the x-axis at -1. My second 0 would be x equals -5. Now, this shows up twice. It has an exponent of 2. So another way to think about this function would be x plus 5 times x plus 5. So we say that that 0 shows up twice. It has a multiplicity of 2. That means that the graph is just going to touch the x-axis at -5. All right, let's try a couple more here. All right, on this one, I again have 2 zeros. Right, so I'll get x equals +3 from this one. It has a multiplicity of 3, and that's odd. So whenever we have an odd multiplicity, the graph is going to cross the x-axis. My other 0 would be x equals -1. It has a multiplicity of 1, which means it will also, or the graph will also cross the x-axis at that point. Okay? One more. So why don't you guys try this one? All right, here we actually end up with 3 different zeros. Setting -x squared equal to 0, right? If we do that, well, I could divide both sides by -1. I can take the square root of both sides and get x equals 0. Okay, so x equals 0 is my first 0. It has a multiplicity of 2, right? It's showing up twice, which means that my graph is only going to touch the x-axis. My next 0 is going to be +9. It has a multiplicity of 1, which means the graph is going to cross the x-axis since that's odd. And finally, I'll have x equals -1. Its multiplicity is 2, which means the graph just touches at that point. All right. So next, let's go backwards. Let's go in the opposite direction. Let's say, given a graph, write our function. Okay, so the directions say we're going to use the smallest possible degree. So what that means is if the graph crosses, we're going to assume that the exponent on that factor is just 1. And if the graph touches, we're just going to assume that the exponent on that factor is 2. All right, so we have 2 zeros here. Right, the first one is at -2. So if I'm writing my function, I'm going to have a factor of x plus 2, right? Because we're thinking opposite sign for our factor. Because if I set this equal to 0, I would get x equals -2. The exponent on that, since it crosses the x-axis, is just going to be 1. Now, my other 0 is over here at +2. So the factor for that would be x minus 2. Now, this time the graph just touches there. That means that I'm going to have an even multiplicity. We're going to assume that any even multiplicity from a graph is just 2. So that takes care of my zeros. Now, the other part of the directions say our leading coefficient is either 1 or -1. That has to do with end behavior that we talked about in the last lecture. So here, this function, right, is going to be odd degree. We've got 1 plus 2, so it's odd degree. And as x goes to negative infinity, f of x goes to negative infinity. As x goes to positive infinity, f of x goes to positive infinity. If we think back to our end behaviors, that means that my third degree function or odd degree function is going to be positive. Okay? So my coefficient here is just going to be positive 1. So this would be my final answer for writing the equation of this graph. All right, let's try another one here. Right, on this one, we have 3 zeros here, here, and here. So the first one is at -2, so that factor would be x plus 2. The graph crosses there, which means the multiplicity will be odd, so we're assuming any odd multiplicity from a graph is 1. My next 0 is at 0, so just for the sake of being consistent here, I'll write it as x minus 0. And the graph just touches there, so even multiplicity. And then finally, I will have x minus 2, and that is an odd multiplicity. So the exponent is 1. Now, to take care of my coefficient of 1 or -1, we have to think about end behaviors. This is going to be a fourth degree, right? 1, 2, 3, 4. So as x goes to negative infinity, f of x goes to negative infinity, and as x goes to positive infinity, f of x goes to negative infinity. If we look back at our end behaviors, that is a negative even degree. Okay, so here in this case, we would need a negative sign out in front. And we can clean this up a little bit. Okay, this x minus 0, we can just write that as x squared. And generally, if we have a variable by itself as a factor without adding or subtracting anything, generally we write that in the front. Okay, so this would be the cleaned up version of this. This still isn't wrong, okay, but this looks a little bit nicer. All right, so next, let's say given this function, we want to sketch a graph. Okay, to do that, we're going to kind of put together everything we've talked about in 3.2. So the first thing I want to do is factor this to make it look like something like this. Okay, so the first thing I want to look for whenever I'm factoring is a GCF, and I can see that I can take an x squared out of everything here. So I can make this x squared times x squared minus 2x minus 8. So now I want to try to factor this. So I'm x factoring. I'm looking for two numbers that multiply to -2 that multiply to -8 that add to -2. So those two numbers that multiply to -8 that add to -2 would be 2 and 4. And we would need to make the 4 negative, right? -4 plus 2 is -2. -4 times 2 is -8. So this would factor into x squared times x minus 4 times x plus 2. So now, what this tells me is where my zeros are. I have a 0 at 0. I have a 0 at +4. And I have a 0 at -2. Okay? Now, the other key thing that we need to think about is end behavior. All right? This is a positive fourth degree function. So it's positive and even degree. If we look back at our end behaviors, that's where both of my end behaviors are going to positive infinity. All right? So now, what we're looking for when we're sketching this rough graph is that we have the correct end behaviors, and then we take into account the multiplicity of each of these zeros. So what that means is, so my first zero on the left side here is at -2. It has a multiplicity of 1. That means that my graph is going to cross the x-axis there. The next zero is at 0. It has an even multiplicity. That means the graph is just going to touch there and then bounce back down. My final zero is at 4, which means, and the multiplicity is just 1, so that means the graph is going to cross there. Okay, so that's going to be what I'm looking for in this section when we're sketching a rough graph. The correct end behaviors, the correct zeros, and then taking into account the multiplicity of each zero, whether the graph should cross or touch there. Okay, now the again, this is called a rough graph because we don't know exactly where the graph is going to go up here or how far down it's going to go down here. Right? What we're just looking for is end behaviors, the correct zeros, and whether the graph should cross or touch at each of those zeros. All right. The final idea that I want to take a look at is the intermediate value theorem. So this just says that if we have a polynomial function such that when we plug in two values and they have opposite signs, so let's say I plug in 1 and I get 4, and I plug in 2 and I get -3. If my outputs have opposite signs, that means that the graph has to cross the x-axis somewhere in between them. Right? That means there's at least one number c between a and b such that f of c equals 0. So an example of that idea, okay, is given this function, we want to show that it has a real 0 between 1 and 2. So what I'm going to do is evaluate f of 1 and f of 2. So f of 1 is going to be -2 times 1 cubed plus 4 times 1 plus 5. So that'll be -2 times 1 is -2, plus 4 is 2, plus 5 is 7. And then if I evaluate f of 2, that'll be -2 times 2 cubed plus 4 times 2 plus 5. So 2 cubed is 8 times -2 is -16, plus 8 would be -8, plus 5 would be -3. So what we're saying is that since these have opposite signs, this is saying the point 17 and the point 2, -3 are on this graph, right? So, I mean, visually, we're saying 1, 7 is on the graph and 2, -3, right? I have no idea what this graph is going to do in between these 2 points, but I know that no matter what, it's going to have to cross the x-axis somewhere to get from this point to this point. I don't know where that occurs, but I know for sure it's going to happen somewhere between 1 and 2, right? Now, in the book, you are going to be asked to estimate that 0 to 2 decimal places. So I want to show you how to do that on the calculator here. Okay, so I've already put this function into the calculator. And if we go to the graph, we can see that the graph does in fact cross the x-axis somewhere between 1 and 2. Now, to find out exactly where that is, I'm going to press the second button and trace. I'm going for this calc menu. So second, trace, and then I want to find a 0. So I'm going to choose the second option here, and it's going to ask me a couple of questions. It's going to ask me to choose a point to the left of that 0. So I just want to make sure I'm somewhere to the left. And then it's going to ask me to choose a point somewhere to the right. So there's a point to the right. It's going to ask me for a guess then. I can kind of move the cursor kind of close to it. The guess doesn't really matter. And then it's going to tell me where that 0 is. Okay, so estimating that 0 to 2 decimal places, we would say it occurs at x equals 1.83. All right, so that is it for this video. The final question is going to pop up asking you what questions you have.